Hmm. Oh, hello there. I guess what's going on? Memes here. We're back. We're going to cover a little bit of uh, astronomical news and stuff, just because. Listen. Number one, apparently, according to the internet, you need to get in the algorithm into. This is actually something that interests me, just because I don't know about you all, but when I was growing up and we went to school, and people would explain, it's like, what is a black hole? Actually, God, I'm so old that I still remember when folks were actively talking about it, that folks would say, it's like, well, there may be a supermassive black hole or ultra dense compact object in the center of our galaxy. And people were actually kind of hesitant about that because we didn't know. And people generally would go, we tend to think that. And I've grown to the point where, like, fast forward like another 20 years, it's like, oh, there appears to be a supermassive black hole in the center of every galaxy. And then occasionally, oh, maybe it got drawn out. Maybe there's the final parsec problem. Maybe there's other things going on. So it's interesting to at least exist so long to go through the different discussions about what may or may not actually be happening. And you go back and it's like, at least when I was taught, it's like, how do you get a black hole? Well, you get an older star. It's running out of like hydrogen and helium to fuse, and eventually you're getting heavier elements, and then it's like it just ends up gravitationally collapsing because it's no longer able to withstand the pressure of all the mass of its outer layers, and basically that initial fusion of hydrogen into uh, helium, and then it goes to helium to oxygen or no, I think carbon, and then you get oxygen and everything after that. Long story short is massive thing. It collapses. It goes kaboom, and then we'll see this massive light show. Illumination at times greater than the entire galaxy. Fantastic. But people have also theorized that, well, maybe there's a particular mass range and circumstances where these things may collapse and you don't have a ginormous cosmic kablooey. That may or may not be the technical term. Again, I'm not a cosmologist. That's Professor Brian Keating. Um, quick shout out there. But I find it interesting because let's start to get into. Oh God, I closed the appropriate tabs. Yes, they're totally inappropriate. Where are we? Which one? Okay, direct collapse. There we go. And of course, the relevant links are in the doobly doo below. Okay, so let's go. We've got some articles. We have an original one that was posted on was it well, it looks like a Harvard educational website, and this was actually oh, we actually got Martin Rees on it. So he was one of the progenitors, and I think he had won the Nobel Prize. Oh wait, hold on. Which one is this? Martin Rees. Okay, so this is the Lord Martin Rees. Okay, I which other one? My cosmology Rees, because I know there's another one, and it's a different gentleman. Hold on, Rees, dark energy. I mean, I might just mean. Okay, one is Adam Rees, spelled Ries, and the one on this paper I should probably actually share with the class. Let's go over here, window. This is Martin Rees, 2 E's. Okay. Long story short is one is this guy, and Adam Rees. I just Adam. Okay. The other is this gentleman. He's one of the gentlemen that did the calculations. I was going to say Nobel for discovering the cosmic speed. And basically, back in I think it was '99, he was analyzing the data. It's like We assumed that the universe was slowing down in its appeared expansion. At least at that time, it kind of appeared like it was speeding up. So him and his collaborators and everything, they won Nobel Prizes and stuff like that in physics, or yeah, basically for the discovery of dark energy, which many people would purport to be the cosmological constant. And again, not all. It's hey, not everybody agrees on stuff. That's why I call it theoretical physics. And there's certain foundations, and who knows? Hey, maybe we'll have to reinterpret some things. But I'm making the general thought that I think most of these things are probably really telling us something, and interpretations may vary. But we shall continue. All right. So what the heck is a direct collapse black hole? It's one of those words where basically it's telling you exactly what it is. Okay. So again, it's our friends at Wikipedia. Feel free to take that for what it's worth. Links in the doobly-doo, of course. All right. Direct collapse black holes. DCBHs. Oh, God. If anybody spent time in corporate America, you eventually start seeing all these acronyms and you start to get confused. I'm sure it's just me. Are high mass black hole seeds. Black holes that will later accrete to form supermassive black holes that form from direct collapse of a large amount of material. I mean, isn't that pretty much like every black hole? If you give it enough time, and assuming it doesn't evaporate, but then again, maybe it does. I personally have opinions where I'm like, well, does it ever actually fully evaporate? I don't know. I can't say. I'm not there. Okay. They are putatively. It sounds like generally considered. Okay. Formed within the redshift range of Z15 to Z30. I'm not sure why. Okay. When the universe was about 100 to 250 million years old. Okay. I feel like this might just be an older article because I'm not sure why it would need to be that far. Are we assuming it's like first generation stars, even though if we're observing it, or excuse me, population one stars are the term. Basically, stars that are only hydrogen. We haven't really seen them. Maybe we have. There's some more speculation there. All right. This is around the same time that stars were being formed, meaning that these black holes could not have formed from stellar collapse. Oh, I think this article might need some updating. Oh, really? Oh, this is all right. 219 retrieved 226. This article might need to be updated. Seems from the first population stars known as population 3 stars. Excuse me, population 3 stars. That's what I meant. Which are technically the first stars. Which, yeah, certain things certain terminology is confusing. Kind of like it was like dark energy, dark matter. People seem to confuse those things all the time. I heard Professor Tyson, Neil deGrasse Tyson, at one point, he used a term on one of his Star Talk episodes when they're talking about dark matter. He's like, to be fair, it's more appropriate term would be dark gravity, whatever that may or may not be. Terminology, it's again, you call it matter because we assume it's a dark mass effect. Now, again, personally, I feel like we should rename quote unquote black holes to mass holes. As a longtime Massachusetts resident, I would say that I'm biased. People have been calling us that for years. So, okay. So this is getting very interesting. So at least the claim is the recollects black holes are massive black hole seeds theorized to have formed in high redshift universe. And typical mass is about 10 to the 5 solar masses. So about was it 10, 100,000? Yeah, so basically 10,000, about 10,000 solar masses, spanning between about 10, 100,000. Okay, no, that's 100,000. Okay, so could be 10 to the 100,000. I don't know. That's a 10 with 4 zeros. 10 with 4 zeros is 10,000. Okay. 10,000 to like a million solar masses because 6 zeros and then a 1 is a million. All right. The environmental physical conditions to form a direct collapsed black hole as opposed to a cluster of stars are the following. The claim is metal-free gas, gas containing only hydrogen and helium, atomic cooling gas. Okay. Sufficiently large flux of Lyman-Werner photons in order to destroy hydrogen molecules, which are very efficient gas coolants. Okay. The Lyman-Werner photon is an ultraviolet photon of the energy range. Okay, so basically twice that of an electron. Okay. Corresponding to the Lyman range and the Lyman and Werner absorption bands of the hydrogen H2 found. Okay. So basically it's, I believe the difference between that is probably going to be something like the fine structure constant because those are like the different orbital levels of hydrogen. Hold on. So say again. So 11.2. So 11.2 electron volts. Just double check from alpha. All right, so that's the band gap of silicon up there. All right. So then 13.6 is a notable. Yeah, the Rydberg energy, which is basically, yeah, I'm sorry. Anytime I see something like 2.17, I'm like, oh, is that the Planck mass? But yeah, basically it's the Rydberg energy. So it's Rydberg energy. That's like the transition level for, I think, hydrogen. Is a physical constant representing the ionized energy of a hydrogen atom in its ground state approximately. Okay. Defines the scaling factor for atomic energy levels. Okay, so the difference between that and that. Spectral lines and stuff. All right, cool. Where are we? Okay. These can, okay. And again, I really think this probably really needs an update to what's going on, just because there appear to be much more recent things that might be rewriting the quote-unquote textbooks on this. The claim is these conditions are necessary to avoid gas cooling and fragmentation of the primordial gas cloud, which could lead to star formation. Unable to form stars, the entire gas cloud undergoes gravitational collapse, reaching extremely high matter density at its core on the order of 10 to the 7 grams per centimeter cubed. That's interesting. I did not know that. So that would be, oh, that goes up. So if we did grams, we swapped that to kilograms, I go up by 1,000. If we swap that to meters, hold on. So 10 raised to the 7 grams per meter cubed. 10 to the 10? 10 to the 10 kilograms per meter cubed. And again, that's a generalized, hypothesized order of magnitude, but I don't know. Maybe it's just me. I get a little giddy when I see something even. It's like, oh, look, 10 to the 10 kilograms per meter cubed. Mass density. Seems to be a nice even number. And again, we don't know. Let's go back to our article. So in a central temperature as high as, oh, look, 10 to the 10 Kelvin. So that's 9 zeros is a billion. All right, so like 10 billion degrees Kelvin. It's pretty friggin' hot. 10 to the 10 Kelvin. For reference, 10 raised to the 10 Kelvin. Okay. Oh, look. That's ultimately at least conjectured to be the temperature of the universe about 1 second after the Big Bang. That's pretty hot. It's like 22 orders of magnitude below the Planck temperature, but let's see, Planck temperature. That's 10 to the 32. Kelvin's difference. Yeah, 10 to the 22. Kelvin's difference. All right, let's go back over here. The occurrence of the general relativistic instability, as well as the absence of the intermediate stellar phase, led to the denomination of direct collapsed black holes. In other words, these objects collapse directly from the primordial gas cloud, not from the stellar Oh, geez, I think they really got to read through this article. Okay, so a computer simulation reported in July 2022 showed that a halo at the rear convergence of strong, cold accreting flows can create massive black hole seeds without the need for ultraviolet backgrounds, supersonic streaming motions, or even atomic. Wait a second. Okay, here we go. So we got the model that seems to be contradicting in the early assumptions. Cold flows produce turbulence in the halo, which suppress star formation. In the simulation, no stars formed in the halo until it grew to 40 million solar masses at a redshift of 25.7. The halo's gravity was finally able to overcome the turbulence. The halo then collapsed and formed two supermassive stars that died as these are collapsed black holes of 31,000 and 40,000 solar masses, respectively. That model may have been extremely useful. Oh, geez. All right, we're getting there. Let's see. All right, so direct collapsed black holes are generally thought to be extremely rare objects in the high redshift universe because the three fundamental conditions for formation, as that section, are challenging to be met altogether in the same gas cloud. Current cosmological simulations suggest that DCBH's direct collapsed black holes could be as rare as only about 1 per cubic gigaparsec at a redshift of 15. The prediction on their number density is highly dependent on the minimum flux of Lyman-Werner photons. Okay, so that seems to be one of the methods that they're going about to try to gather the information. It can be as large as 10 to the 7 direct collapsed black holes per cubic gigaparsec. Okay. So 10 to the 7. So 1 followed by 7 zeros. That's 10 million. So the general, at least according to Wikipedia, thoughts for the number of potential direct collapsed black holes per gigaparsec. So basically per billion parsecs, somewhere between about 1 to 10 million. That's a and again, it's a very large area, but it's not infinity. So between 1 and 10 million. It's a rather broad range, wouldn't you say? And again, that's an observer like me. I'm inputting my human built-in typicalities to what might be going on. Okay. A study using the Press-Stecher formalism is a mathematical model for predicting the number of objects of certain mass within a given volume of the universe. Okay. Okay, that suggests formation scenarios may account for a significant amount of supermassive black holes. Previous research on the formation of direct collapse black holes at high redshifts greater than 13 support this model, indicating that direct collapse black holes formed abundantly in the early universe at redshifts around 0 to 14, with the presence, this process which peaked at there. Okay, so they're saying there's a particular combination of circumstantial events, as they went over there, the prerequisites required that may or may not be lax depending on which interpretation you have is it should be metal-free gas, aka if you're an astronomer or cosmologist, anything above helium is considered a metal. Why? Generalized convention. Okay, so you need atomic cooling gas, so hydrogen is good at that. And you need to have a large flux. So basically, you're going to need to have photons of that range to basically. Okay, so hydrogen molecules are good at effectively cooling. Because basically, if you get a hydrogen and another hydrogen, it usually just likes to come together to create H2 or hydrogen 2 there. And apparently, that's very good at cooling it. So if you can get enough photons of that to basically help break apart the hydrogen molecules, it can't cool. So it's going to be more likely to undergo an extremal event. That's my interpretation. Again, I'm not a cosmologist. Okay. We went through there. Okay, so let's actually get to the detection. All right, 2016. Team led by Harvard University astrophysicist Fabio Pesciucci. Was this on him? No, he's not on that one. This is from 2006. Okay. Identified the first two candidates direct collapse black holes using data from the Hubble Space Telescope and the Chandra X-ray Observatory. The two candidates both have redshifts of, about 6. That seems to be a lot less than about 13. Oh no. We might need to amend some models. How dare you, observationalists? Two candidates that have both greater than redshift Z is greater than 6 were found in the Candle's Good S field. The cosmic assembly near infrared deep extragalactic legacy survey. Candles. Okay, so it's the largest object observed by the Hubble Space Telescope. Okay, 902 orbits of observing time. That sounds really, it sounds like a lot. Does that mean it just went around the Earth? Wow. Good S field. All right. Great Observatory's Origin Deep Survey. Okay, I can see why they call it the Candle's Good S or Candle's Goods field and match the spectral properties predicted for this type of astrophysical source. In particular, these sources are predicted to have a significant excess of infrared radiation when compared to other categories of sources of high redshift. Additional observations, in particular with the James Webb Space Telescope, will be crucial to investigate the properties of these sources and can confirm their nature. Okay. So as we can see here, what's the difference? We've got like 6 or 7 lines here because not a ginormous amount of information. All right, a primordial black hole is the result of a direct collapse of energy ionized matter or both during the inflationary or radiation dominated eras. A direct collapse black hole is the result of the collapse of unusually dense and large regions of gas. A stellar black hole first was in a stellar phase when it has undergone nuclear fusion. Wait, hold on. A stellar black hole has a stellar phase where it undergoes nuclear fusion. That you mean star? Okay. It goes nuclear fusion. Once the star's core has fused its available light elements and is unable to fuse heavier elements in its core, it goes supernova and produces either a neutron star, which can evolve into a black hole for accretion, or into a black hole. Okay. Here's my question. How many neutrons does it take to a neutron star for a neutron star to become a black hole? Imagine this as a quote-unquote Duncan or thought experiment. Because the interesting thing is, as you add mass to stuff, it gets bigger. You add mass to a neutron star, it gets smaller. Why might that be? Now I have a speculative guess. It's just according to some calculations, the actual radius of a neutron might actually be a wee bit smaller than that of a proton. That's more massive. But if this is what we observe from neutron stars, isn't the easiest solution just, well, it's because when you have a neutron star, when you go into some of the literature and stuff, it's like, well, yeah, there are actually some protons and other stuff there. But as it gets more and more gravitational energy, they just seem to, and those protons end up kind of becoming neutrons. Or I might be misremembering this, but it sounds a lot like, it's like, yeah, no, a neutron isn't just when you get like a proton and an electron, you just kind of smush them together. It's last time I checked, it didn't quite seem to say that. But then again, you have reverse beta decay. So your standard beta decay, or like the weak forces, what is it? You get a neutron by itself. For some reason, after about 14 and a half minutes, it just decays. If it's not part of another nucleus or system like that, it just decays. Why? I don't know. The weirdest thing is, depending on how you do the experiment, you literally have a consistent 10-second discrepancy, whether they use, what is it, the bottle trap method, or I think it's another like ionization trap or something. Nobody knows. Maybe somebody does know. Maybe somebody watching now or temporally in the future knows. I don't know. But it's interesting. But then you end up learning, and I learned this after high school chemistry and stuff, apparently, in a star, under the right conditions, you can have reverse beta decay. So rather than a neutron decaying into a proton, a neutron, and an antineutrino. I just say that so many times, that's just kind of ingrained. You can literally have a proton become a neutron, and then I think it emits a neutrino and a positron. I'm just saying that seems to be a thing. I totally didn't know about that until probably the past few years. I'm like, that's amazing. Like, I still don't have an answer to the first thing, why a neutron decays, but it's like, it almost seems to be stars under those extreme conditions seem to be able to almost regulate what they need. It's who imagined that? People smarter than me. All right. Let's actually get to an article. All right. So this again is in the doobly below. As we can see, this is from Mitchell C. Bengelman, Marta Voluntari, and Martin J. Rees. All right. So the abstract is, we describe a mechanism by which supermassive black holes, SMBHs, can form directly in the nuclei of proto-galaxies without the need for seed black holes left over from early star formation. Self-gravitating gas and dark matter halos can lose angular momentum rapidly via runaway global dynamical instabilities, these so-called bars within bars mechanism. I have no idea what that is. Let's find out. No, not those. Okay, it's a data visualization technique overlapping a bullet change. Okay, a metric to a benchmark. Black holes. Okay. Okay. Also, this was 1989. Ah, all right. Usually thought to be powerful accretions of supermassive black holes. Is a theoretical bars within bars is a theoretical mechanism describing how nested rotating structures of stars and gas and galactic centers transport fuel towards inward to supermassive black holes. A large scale. Oh, so basically you've got like a current of mass and energy going towards a strong source of an observed gravitational effect. Okay. Well, it's a NASA's website, so take that for what you would. As proposed, which bring gas in on large scale, the bars, stellar bars sweep the interstellar medium into a gaseous disk, few hundred like parsec in radius. Under certain conditions, this disk can become unstable again, allowing matter to flow inward until turbulent, vicious processes control until turbulent, vicious processes control angular momentum transport. This flow pattern may feed viscosity-driven accretion flows around a super massive black hole, or lead to the formation of the supermassive black hole itself if none was present initially. Okay. It's from Schulman, Frank, and Bengelman. Oh, hey, look. The same author. That is the same author, right? Mitchell, yeah. All right, so this leads to a rapid buildup of dense self-gravitating core supported by gas pressure, surrounded by radiation pressure-dominated envelope, which gradually contracts as compressed further by subsequent infall. We show that these connections lead to such high temperatures in such a region, the gas cools catastrophically by thermoneutrino emission. Oh, if we're emitting neutrinos, there's got to be some form of beta decay. The conversion to maybe neutrons. Okay, go on, my friend. Leading to the formation and rapid growth of a central black hole. Okay. We estimate the initial mass and growth rate for black hole, the typical conditions in metal-free halos. All right, so temperature for that potential condition, 10 to the 4 Kelvin. Okay, that's probably where the Wikipedia article got it from. Most likely to be susceptible to this runaway inflow. So that is 10,000 degrees Kelvin. How hot is our sun? It's like 5,600 degrees Kelvin or something. We usually think, except for the was it the magnetosphere? Sun temperature. The core we think was the corona, yeah, solar corona is like 1 to 3 million degrees, and we had the Parker Solar Probe go through and it detected a 1,000,000 degree photon. It's like, how did this thing not get vaporized? It's like, it had like detected like those photons, maybe like 1 every cubic meter. It's like, okay. So when we're saying 10 million degrees, we mean you occasionally could have a bump there. It's like, that's not quite like the same density of being in a hot tub when you're around 100 degrees. Yeah. Yes, and at 100 degrees, let's lower that a little bit, because if we're talking Kelvin, oh God, I should say, room temperature is about like 300 degrees Kelvin. Okay, 100 degrees Fahrenheit. That's my reference temperature. No, that's about human thing. Okay, probably a little under 100 degrees Celsius. We'll leave that. Okay. All right, it's corona there. Hey, what's going on, Charlie? The travesty of the universe. I don't know about that, man. It's just very interesting. Like, I'm reading the Wikipedia article, and just the quick TLDR is, when you start reading this direct collapse black hole, it's like, okay, some of these things were updated. When was this? Okay, that was 2003. That's from 2000. I think this article might need a lot of revision, because they're going through like theoretical stuff. Okay, so that's 2020. All right, yeah. But most of these things, as far as I know, I think I heard Anton Petrov first say this maybe 2 or 3 years ago. It's like, it appears like there might have been a direct collapse. It just kind of seemed to disappear. There's a bit of a halo, but you didn't have some ginormous cosmic kablooey, which when I was growing up, no, that's how you get it. You need to have that shock factor. But what happens if they were quote unquote idealized conditions? All right, this is 2020. Yeah, initially they're saying it's like, well, this must have formed in the early universe of like redshift of like 16 to 30. Within the same direct thing here, it's like, okay, well, maybe some of these things are maybe redshift 7. You go down further, it's like they had another model. What is it? So the model. Okay, so they've been using Z greater than 13. That's about 15. All right. So, yeah, that's about the same actual detection. Oh, look, these appear to be at redshift for about 6. Well, greater than 6, or at least greater than 6. That seems to be far closer than 10 to the or z a redshift of 14. Like it starts to go up much faster the further back you go. Because if you're using the standard lambda CDM, which of course is not the final say in the model, I mean, we don't know what the dark matter is. We don't know what this observed uh, dark energy is, or to be fair, to quote Neil deGrasse Tyson, dark matter should more like dark gravity. So we don't know what the dark gravity or dark energy observed effect is. So, okay. So we still don't know what about 95% of universe as far as we know is. Maybe there's some slight adjustments. Maybe there's a way we can explain more with less. At this time, I don't believe it's publicly known. There's a lot of speculation out there. I'm happy to entertain speculation, but if we need to add more epicycles to explain it, is it really helping? Maybe it is. Maybe that is the answer. The universe is under no obligation to make sense to us. The sheer fact that we seem to be able to parse what might be going on, and we've actually built technology upon that. That's how people can remote view this from wherever you are in the world, essentially at near the speed of light to an observer like us. Yeah. Don't worry, we'll get into the more juicy stuff in just a moment. We got an article from Universe Today. It's the online periodical that's been run for the past like 20 something years for Fraser Cain, which appears to be like actual space journalists. I may or may not have full disclosure. I subscribed to his Patreon the other day, just because I feel like journalism is important. I talked to him, like he does this little thing where he offers you an interview for like 15 minutes. And it's like I talked to him maybe like 10, 15 minutes. And it's like, how would you improve things? I'm like, have other like maybe smaller channels that are doing the same thing as he's doing on. Now, that doesn't include me. Listen, am I going to say this is high quality space journalism? No. I'm reading a Wikipedia article. I'm going to a journal article from like 20 something years ago. And I'm showing one of the actual articles from Universe Today. Because I think it's good journalism. And I think we need more of that. That's a personal opinion. All right, where are we at? Yes. Welcome, everybody, to the direct collapse black holes that totally are not going to help rewrite cosmology. Here's my thought. And again, I have no idea if this is correct or not. But it's like, if we usually think black holes have a giant cosmic kablooey, as long as we're looking generally in that direction, we're going to see it sometime. Okay. That's fine. Now, if you're having more of these direct collapses, that raises the obvious question. How often does this happen? We may have seen a few things, but we're also seeing little red dots, which there's also, I think, another article here where it's like, what is it? Yeah, little red dots are direct collapse black holes. And this was, oh God, this was literally last month. Okay, because what is it? There's something within astronomy or cosmology. It's like, all right, if you have a single observation of something, it's an anomaly. You have two, you have a set. Once you have three consistent observations of a similar phenomena, I think at that point it actually becomes a thing. So I remember at least one, maybe two over the past year or so, but okay. Again, Occam's razor is if these things, if direct collapse black holes are happening a lot more, it's like, oh, there seem to be a lot of these little red dots around. What might be going on? It's like this seems like it might explain more with less, rather than, oh, you got this phenomenon, you got this phenomenon. Well, what if it was this phenomenon? Oh, look, we can explain a lot more. Now, again, it was proposed. Now, if we see more observational effects and similar things, because again, it might not have the ginormous cosmic kablooey, but from what I've seen, there is still a shell of matter type particulate that is surrounding it. Now, it might not have the violent explosion. There still might be a boom, or, well, in space, you would actually need to have matter to have a boom. So there might be a silent kablooey, but it might not just be the ginormous cosmic kablooey. Again, those are my personal, not so technical terms for it. Okay, so let's see. We skipped ahead. Okay, so this is basically okay. This process would give black holes ample time to attain quasar-sized masses by a redshift of 6. Okay. So a lot of this is thought if you have a direct collapse, it would have to be under initial stages in earlier universe where things were a lot hotter and denser, so you could have direct collapse. Now, it seems to be the case that rather than being at a redshift of like 15 to 30, which is getting back like a lot closer to the beginning-ish state. Like, what is it? Redshift 15 is, was that 6, 7? Oh, yeah. So that's about 12 billion years ago. Oh, it's 30. Redshift Z 30. Oh god. Oh, it's giving a cosmology. Come on. Doesn't even want to talk about it. It's like, no, we don't want to talk about Redshift 30. Let's see what Harvard's got to say. All right. Formation of black holes is 30 with large baryonic. When was this from? Before 1990, after 1990, was before 2000. Okay, March 2014. All right, so that's within, it's a little over a decade ago. Black holes at redshift. Okay, supermassive black holes at redshift of Z greater 6 remain a theoretical puzzle. Well, we might be solving that puzzle. Okay, so all right, so part of it is framed within the question of we believe that perhaps direct collapse black holes may have been a thing to help act as seeds for galactic nuclei, aka the supermassive black holes or ultra compact objects that seem to be at the heart of basically most all galaxies, unless something maybe weird is happening. And again, who knows? Hey, maybe it's just a giant hunk of dark matter that we don't seem to understand. There seem to be these halos around us and everything, and people have come up with all different ideas. We're looking for, like, I don't know, like wimps, axions, wash on, wax off. I don't know. Why? Well, within a lot of physics, what do? We smash some things together. We try to reconstruct what happens and see if we can discover new particles. Because particles are what we often refer to as particles. Perhaps a better term is wavicle, as Matt Strassler might say. Yes, his book is Waves on Impossible Sea. And again, I listened to it while going cross country, and I think he did a pretty dang good job of giving a decent outline without diving into a lot of field theory and math. Again, I'm not going to pretend like I'm a field theorist or something. That was one of the gentlemen that responded with I think Tim Nugent to Dr. Eric Weinstein's geometric unity. It's, I don't know. It's some people, if Poly or something. Oh, that's not a real. I don't know. I just talked to the guy like not that long ago, but whatever. Yeah, the internet's a weird place, my friends. Meet a whole lot of different people, and depending on which perspective you're getting it from, it seems like a whole new world. I think there was a Disney song about that once. A new fantastic point of view. All right, so this affects, all right, blah, blah, blah. All right, so Z equals 6 is less than Z equals 30. All right, so some things seem to be getting a little bit rewritten here. This is interesting. Hey, we're learning. It's a learning process. That's science. We want to cast aside our misconceptions. Why? We want to be less wrong. You have a great idea. It's like, this is fantastic. Now, Stephen Wolfram and Dick Feynman used to have a game that they played. Uh, it was trying to find the fatal flaw in somebody's argument and see who could do it first. Because somebody might go up there and they're talking about all it solves all these things, and you're looking, it's like, yeah, your calculation, what happens? Aren't you assuming this? What if it's this? Everything may come crashing down. Now, a good scientist, if they're pointing out a fatal flaw, and again, I'm not claiming to be a good scientist, I'm a crazy person on the internet. It's that if somebody points out a strategic flaw, you should take note. Now, again, I've ignored some of those flaws just because, well, it wasn't presented in a way that I quickly grokked, or I looked at another fashion. And then later, it's like I go through, it's like, oh my God. Yeah, I would need to assume this, this, and this. Now, maybe it is still the case. But again, if you're looking for the simplest answer, why might it be the case? And that's why personally, it's like, I'm going through, I'm like, well, if I were to believe this, I would need to literally say, like, the meter is meaningful or something. And that seems like a crazy thing to say. But then again, or basically our SI basis unit system is correct, or it makes sense. Now, that's a very massive claim. How do I make that claim? And you go, okay, well, maybe universe holds water. What does that mean? It's, well, maybe if we use a reference density of water, kind of like we initially went through the metric system of, then it was based on a constant of nature. It's a constant of nature at a very particular Earth basis, but it can explain a lot. Maybe that's the answer. Hey, I mean, at that point, you could have your hexagonal lattice and you can deal with all that black body radiation because basically water can act as a black body. Now, that's an absolutely insane idea, but just because it's insane doesn't mean it might not be true. It's, I also just go back to history for that. And again, I'm looking for the easiest ways to try to explain what might be going on. To reconnect that thing before about having to hold water is, I'm like, all right, well, I can do these kind of crazy calculations with the mass of the Higgs. And again, that depends on experiments, and we only know it to so many digits. But I'm like, well, why does this seem to line up with like the elementary unit of action squared when you uh, investigate the squared relationship between the mass of the Higgs boson and the mass, the Planck mass? At least the first three significant digits to come out is 1.05 times 10 to the minus 34, which happens to coincide with the first three digits, and magnitude power of h bar, the elementary unit of action, or Planck's reduced constant, within the SI system. So that's only when it's expressed in joule seconds. Expressed in electron volt seconds and everything, it's like, can you really say it's the same thing? Now, if you were to relate that to 1 joule, there is a difference of precisely 10 to the 7 between like the electron volt second, or, oh, excuse me, erg seconds. Erg seconds, I meant. Apologies. And again, different quantification of numbers there, but at that point, you're inferring a preferential basis. Now, there shouldn't be a preferential basis, to my knowledge, and you need a really good reason for that. So that's why when I do the quote-unquote spherical God cow, it's like mass energy of the Higgs divided by, turned to a literal spherical cow. 4 divided by 4/3 pi r cubed. Where's the r? Let's just use its Compton wavelength. And it comes out to be about 1 reciprocal meter squared. It's like, when you take the square root of that, it seems to be just above 1 meter. I assume that that's where that commonality comes in place. And to be fair, it's probably a stronger argument to saying that some form of gravitationally induced curvature around the meter scale for the Higgs boson is probably a better reason why the meter would be significant rather than our original definition. Our original definition was, well, it's obviously the distance from the North Pole to the equator through the Paris Observatory divided by 10 million. Why? Duh. It's, I mean, talk about an arbitrary basis. And again, it's been refined over the years. We set the centimeter to 1 gram of water at about just under 4 degrees Celsius and at about one atmospheric pressure. And again, it's not quite 1 gram per meter. However, if you do take that particular number and you were to raise the pressure to about 1.5 atmospheric pressures, which again isn't necessarily that much. And again, that's above sea level. Where's most of the water? Under the sea. Again, Sebastian taught us well. It's about under the sea, my friend. Um, oh God, why is it you can pull out like a Disney quote from like almost anything? Oh God, I'm just going to assume. Well, obviously, I must have just been brainwashed. That's obviously the only thing. It's like a macro version of the Higgs. Where are we? Stress testing idea. Well, that's ultimately what it is. It's like you can have an idea, it can be beautiful, but if somebody finds something flaw, and actually, I had folks tell me that, and then one of the more recent things of ChatGPT pointed out, I'm not going to lie. At one point, it was going through some other ideas. I'm like, I really just want nice words said. I'm like, oh, what about this? And it pointed out my flaw, and I'm like, oh, totally has a point. And other people have told me that, but it's like, I'm going to take that seriously. I mean, I could just get mad and say, just chat is just, it's broken, but how can I say it's broken if it's doing calculations that was messing up like 6 months before and now it's doing an incredibly high level job. Like I'm going through, I'm double checking it, like using Mathematica or Wolfram Alpha, and it's like it's with the data it used, it's right. Now, is it right about everything? It's trained on humans. I mean, we're imperfect creatures, so like we're wrong about plenty of things. Everything. Oh, no worries, no worries. Uh, oh yeah, sometimes you gotta mute things. Wait a second. Let me. Oh God, I should check my own broadcast. Wow, am I really that bad? Let's see. Da-da-da. All right. What are we? Okay. All right. I think that's okay. Okay. No, no, no. That was just somebody. Somebody was opening up a package of chips or something. All right. Oh God. No, that happens sometimes. I was trying to salvage a broadcast that is it a Rick had given a presentation virtually at the physics monastery for our last gathering, and I feel like it's a very relevant thing that he had done back in what's it like November. Yeah, I think it was beginning in November, August, October, November. He had given that talk. I was going through and I'm like, all right, let me try to update this. And it's like, I can't get it. And then I see a recent, seemingly, in my opinion, overlooked result that some physicists did with Boltzmann's constant about statistical games of dice. And I'm like, oh, I feel like we may have already. I felt like I need to have Rick do it again. And again, he did it privately with me once, but I think it might help explain a lot, especially perhaps within the coming months. We shall see. All right. Again, the common question: what the heck is the Compton wavelength? That appears to be the limit at which a particle has particle-like property. Now, it so basically, if you were to get greater than the Compton wavelength, particle doesn't really have particliness anymore. That's the best way I found to say it. And again, I'm mostly just stealing that from Professor Sean Carroll. And even when I'll have discussions within chat, I'm like, well, I kind of heard this. I kind of heard this. What happens with this? Maybe there's a computational thing here. Um, it's gotten really good. It's gotten really good. It's terrifying. And just even at simplifying, I was reviewing some stuff for charged rotating black holes. So it's like a black hole that had a lot of times people just do the Schwarzschild solution, which is you're trying to do its radius. It's like 2 gravitational constant times your mass divided by c squared, and you'll get the Schwarzschild solution for a non-rotating, non-charged black hole. And its event horizon will be like 2 Planck lengths for every Planck mass that goes in there, which seems like be a factor of 2. And a lot of times people will use that. It's like, all right, cool. No, it's spherical. That's literally just the core spherical cow, you could say, because you're assuming a sphere, typically. But then very interesting things happen when you add an angular momentum and charge. And then we ask ourselves that, okay, so if black holes or something like black holes, whatever they may or may not be, okay, we have a solution, an idealized solution. It's not rotating, it's not charged. Now, have we ever observed that? Of these things that we believe to be black holes? Don't think so. I haven't seen any data. Maybe it exists. But if we're going to assume that, well, every black hole, whatever again it may or may not be, ultra compact dense object, it's going to have these properties, and we've never seen them not rotating and or without charge. Because if you're going to get rotation, you're going to get some stuff around it. It seems to gain some charge. Wouldn't it actually be better to maybe take it to the limit of things we've observed? Just a thought. Some weird things happen if you take it to its limit. Pardon me. I need a hydrating caffeinate. So ultimately, Charlie, the thing that I learned the other day, hold on, let's just go to this. So basically what I had been doing is I was just doing the whole, was it Higgs boson, speed of light squared. So that's mass energy of the Higgs divided by 4/3 pi r cubed. R cubed is the Higgs Compton wavelength. This is mostly just a fun calculation, just because it gives you something about order of magnitude. So again, hold on, I didn't put an exponent. Oh, geez. Friends like these. Oh, wave. What? What did I do wrong? Should I space it out? I'm pretty sure that's... No, let me take that part off. Oh, nope. Come on. Okay, it understands. Yeah. Divide. Maybe they're updating. Wow. Yeah, it is. I mean, am I just confusing it by putting that on there? Occasionally, the syntax does matter. Oh, God. Oh, hold on. Higgs boson, Compton wavelength. Okay. Maybe that will help. It's more specific. Because sometimes... Oh, hold on. Wait, hold on. Higgs mass. Okay. I didn't. It was user error. I used the incorrect syntax. I was supposed to put Higgs mass times c squared to get its energy. Okay. I confused it. All right. So it's the whole... If you do that, you multiply it by the Einstein constant. Actually, it's more for the dramatic effect. So let's just throw some protective brackets on either side. Boom, boom. All right, got that. So if you divide into the universe vacuum energy density, universe is vacuum energy density. See, I'm very easy to get off track. So who doesn't love talking about stuff that they play around with? All right. So the interesting thing is I got this number. I'm like 1.1 times 10 to the minus 52. I'm like, why does that look familiar? Well, Cosmological constant. What's that? 1.1 times 10 to the minus 52 reciprocal square meters. So it's missing the units. It just happens to share the beginning magnitude. And again, there's a little bit of a rounding error there, but it's pretty close. And then when you take off the vacuum energy density, and instead, if you multiply it by the Einstein constant, okay, so we want the C4 constant, speed of light to the fourth. The weird thing is, wait a second, gives us approximately 1 reciprocal meter squared. Wait a second. Those are the units we were missing there. Might there be a coincidence? I don't know. Again, it was cool enough to go into paradigm drift and kind of share this. It's like, this is an interesting thing. Why is it a thing? Seems to be coinky, and that's why when I the closest I can get down why this might be the case is this just happens to be what comes out for the Higgs boson. And again, most of the things within the quote unquote weak sector, the Z boson, the W boson, they're going to be kind of close to a meterish there. And again, this is just using the quote unquote spherical God cow. The typical way of doing this, and I totally forgot this because chat helped teach me this as I was going over constructing like the Higgs mechanism in a Lagrangian density. Normally what you do is you take the energy of a thing, you raise it to the fourth power. Okay. Why? Because 3 plus 1 dimensions of space-time. So all right, we got 4 dimensions in which we live. Let's raise it to the fourth power. You're gonna get it's the Quartic-Cauchy coefficient. Why? Because that's what it tells me. Now, the thing is, if you want to normalize this, so to speak, typically you're going to divide by other constants in nature with units multiplied or divided by them, something like that. So what you do is, long story short, you divide by h bar c. So Planck's constant times the speed of light. It's the gravitational constant with the Planck mass upstairs that we know to a lot more digits. Oh, excuse me. You need to divide it by, if we're raising it to the fourth power, you need to cancel this out so you get 1 remainder. So basically, we want this Higgs mass looking, this is another method of calculation, what type of curvature it might have. And again, I might have used a slightly wrong term there. I apologize. I'm not a quantum mechanic. So whatever mass energy you have to the fourth, you're going to divide by this h bar c raised to the third. So to the fourth, to the third, gives us this. What is this? It gives us a number, and the thing that blew my mind is this had like 1,000 difference from the other thing, but all it is it's the reduced spherical God cow. Why? So we're not going to turn into a spherical God cow, and we need the reduced Higgs-Compton wavelength. We'll do the reduced. Let's see. I don't think it's going to pick up on the syntax unless it's changed in the past few days. Nope. So basically, to reduce the Higgs-Compton wavelength, it's just the wavelength divided by 2 pi. So it just, yeah. So rather than taking like a circle, this would be like the Compton wavelength. The entire circle, we're just basically going to take the radius there. So, and again, that kind of makes a lot of sense. So divide by 2 pi, brackets there, another one there. Okay. So when we do that, thing there, we want the Einstein constant to the fourth. Oh, wait, let's just take that out. So if we look at this, 5.1 times 10 to the 45. 5.1 times 10 to the 40. It's the same thing. So that's standard convention. And because when you do it definitionally, Hans had pointed this out to me. You've got Planck's constant, and then you divide by a mass and the speed, you'll get its wavelength. If you use a reduced Planck's constant, which is h bar, it makes sense. So I call it a reduced spherical cow. Really just a cubical cow. But I don't know. I use spherical, and I like plays on words, so squarical. It also sounds a little bit like Squirtle. So maybe we'll do some memes about that. Yes, Pokemon are invading. Decelerate now. What are we assuming there, Charlie? Because thought good old Newton, he was like, object in motion tends to stay in motion. Now, you also point out one of the big things for, okay, assume we could travel at some large percentage of the speed of light to get someplace. Fantastic. One that needs to slow down. That's often the overlooked issue, because you probably have to start slowing down a lot sooner. Because let's just say you had, like, in a lot of these sci-fi things, okay, you instantly stop. Now, number one, you got to somehow protect your own vehicle. Okay, now you do that. Maybe there's a warp bubble. There's a warp bubble. Okay. Now you have an accelerated object that stopped. So isn't that going to maybe create a, I don't know, a space-time shockwave that's going to destroy whatever's in front of you? Now that might be a great tactic if you're trying to obliterate things, but if you're trying to colonize a planet, you get there, it's like, what happened? We arrived. Oops. So that's let's see. That's the contemplation. There might be something there. I really haven't thought about it. That's some interesting, because here's the thing. There's one thing I've learned. Questions, the proper question makes a huge difference. It's one of the things that Einstein is attributed with saying, it's like, Professor Einstein, you have 1 hour to solve a question to save the world. How would you do it? I would spend 55 minutes composing the appropriate question and 5 minutes answering it. Basically, more or less. So yeah. So long story short is the whole way I think that 1 meter might be built in is, if you just assume it was like literally a spherical cow, you take the root of that. It's literally pretty close to a meter. What happens if we define the meter precisely as that? Would things make more sense? Again, if you want to set a definition, you probably need more than three to five significant digits. At least the speed of light, we got to like 9. H bar, we got to 10. We defined it. We had it to 12, but last 2 digits, that's a pretty large error bars. Or, oh God, I'm old enough to have gone through the calculations when it was like that. Okay, I'm realizing I didn't even get to the Universe Today article. Let me check one thing. I told Sebastian that I would help him with some stuff. So, Discord. I swear I could spell Discord. Don't mind me. So here's what we'll do. We'll go until Sebastian is gone. So go when you are. Okay. So long story short, we're gonna go until Sebastian is here, if he is. Okay. So let's go to the actual. I'm realizing I should probably move this somewhere where I could actually notice, rather than having all my notifications off. All right, there we go. So this is brought to us by Evan Go from Universe Today. All right, here we go. No supernova needed. The star collapsed directly into a black hole. Well, I mean, that seems to be the story in a nutshell. All right. So in this illustration, the stars collapse directly into a black hole. The black hole is surrounded by the star's envelope, expelled prior to collapse. A white ball of heated gas in the center is falling into the black hole. Direct collapse black holes shouldn't be that rare according to theory, though observational evidence is scarce. Well, minus the cosmic kablooey, If it's ridiculously far away, then yeah, it might be hard to see. All right, theory shows that stars can collapse directly into black holes without first exploding as supernovae. In fact, this should be a relatively common occurrence, but despite that, astronomers have found scant observational evidence to support it. Now, I am just a crazy person, but isn't there an issue with like missing stars? Like, we have these stars in like old photographic plates. We go to look now. Some of these stars seem to have mysteriously vanished. We didn't see a cosmic kablooey. Listen, I ain't no Sherlock Holmes, but I'm like, well, if this is a thing, and it seems to be, we allege it's a common thing, could this be the thing and the reason the stars are missing? I don't think we need busy time mysteries to investigate the call of the missing star. Maybe we do. Maybe we do. I don't know. Maybe we need to say hooray for Huckle, bring in the crack team, and I'm pretty sure we have like a lot of scientists. Like it. Listen, I can guarantee you, I'm not the first one to say this. I'm a crazy person on the internet. I'm pretty sure there are a lot of scientists that have maybe said this. Maybe there are a lot more papers than this, or not like anybody would ever not say anything because they're afraid of getting bullied or something. I mean, we like sharing scientific ideas. It's not like we would refrain from sharing an idea because it might upset our friends. I mean, it's not like they have work that has a particular perspective. And if we propose this perspective, it might throw them for a loop. They might not want to collaborate. And now again, that would be a human problem. And again, that's why I've kind of gotten away from humans. And because reality, the fabric of reality seems like this might actually be more easy to do it than human beings, because human beings are complicated. Keywords, emergence, this, that. I don't know. All right. Where are we here? I'm sorry, I just ranted. Again. Okay, but it might have happened in our neighborhood. Haven't there been little red dots located along the way? I mean, how long have we had telescopes and people actively look? Now, we've had people actively looking for like thousands and thousands of years. You go back to like 1000 AD, and you still have like Chinese astronomers that have noticed supernova and stuff. So there have been people looking for a very long time, and we do have records, but it's like, if we're going to keep like 1,000 or 2,000 years of records versus the currently accepted age of universe, which is like 13.7 billion years. Maybe a little bit has happened in that bit of time where we haven't had high-powered objects looking at the cosmos. Again, I say this as just some meat suit just remotely talking to you across the internet stuff and things. All right. Maybe having the Andromeda Galaxy, and astronomers almost missed it. All right. So in 2014, NASA's Near-Earth Object Wide Field Infrared Survey Explorer, NEOWISE, observed a star in Andromeda becoming more luminous in the infrared. These observations were contained in the data collected by the telescope and only uncovered recently. The astronomers were filtering NEOWISE's data for variable sources and discovered M31-2014 DS1. A supergiant star in Andromeda that appears to have collapsed directly into a black hole. But the redshift, that can't be. It's not even greater than 6. It's supposed to be 15 to 30. What's going on? I don't know. I'm sorry. I'm being disrespectful. And again, I'm coming in here where I've already heard about those things, so it just seems obvious to me. I don't know. The researchers, but we don't know. We do not know. We just have evidence purporting this is the case. Well, we might have theoretical calculations. Might have a beautiful theoretical calculation. Doesn't mean it's true. Maybe it is. It's a follow experiment, as my friend Sam would say. The researchers examined sequential images of M31 looking for variable sources. Images were taken every 6 months from 2009 to 2022 using the 6-month cadence observation. Okay, so they basically do the observations every 6 months. We searched for luminous mirror transcendence, which would accompany massive infrared transients, something like that. Accompany dusty stellar eruptions, such as a failed SNE. Supernova explosion. All right. They found M31, blah, 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 and over a 2-year period, blah, the source increased its mid-infrared flux by 50%. 2 years of brightening, it faded below its initial flux. In 1 year, the fading continued until 2022. Okay. So it looks like it just kind of faded away, or it's a lot less intense. So it showed the gradual. Okay, so this is all right. So 2012, 2016, 2022. Okay, so okay. It seems to be getting smaller. If that was a supergiant, its luminosity seems to be fading away. All right. As you can see, this is the quote is, "This has probably been the most surprising discovery in my life," the lead author Day said in a press release. The evidence of the disappearance of the star was lying in public archival data, and nobody noticed it for years until we picked it out. So this is probably one of the big cases for a lot of AI, different programs, because there's one thing it's good at, it's picking up patterns. Now, a lot of this, you need to go through it like with humans. So compare this, compare this, compare this, compare this, try to overlap, try to look at it as best you can. If we have, and again, this has been just chilling for years in publicly available data. It's like, I suspect, I don't know, but I suspect things are going to start to pick up, and we're going to learn a lot more in a very short period of time. And again, there'll be people that will disagree. And again, maybe it's all for naught, but I think a lot of things are going to be continuing to change. And was it the Rocker Poly? Some ways it said this, and again, I don't really condone this, but I'm like, the quote is something along the lines: "It's physics moves forward by one funeral at a time." Why? Well, the prevailing thought period. This person has clout within the thing. Now, what I tend to suspect is, if certain data starts to come in very quickly, if certain folks held particular ideas and those ideas are beginning to become untenable, we just might see a lot of people retiring early. That's a rampant human conjecture. I have no idea for that. Maybe it's completely wrong, but how are you going to argue with data if you've built your life on being a scientist? You say you don't like it, that's fine. It's not a good excuse. It's not a good argument. And again, I'm sure the good scientists, they're going to be able to figure out what's going on, because as things go on, it's like, you're going to be in an old paradigm, let's say, and well, if you've got a very bright young person and they would like to make a name for themselves, and if a lot of folks are just like, well, this person's was really smart on a lot of things, and they can show that your perspective don't hold water, so to speak, that might be embarrassing to some people. Now, again, you don't need to do that. You just present the data. That's all it is. You just go through what's actually going on. I'm sorry, I'm continuing to ramble. Okay, so this region, basically the Andromeda Galaxy, is well observed by other ground and space telescopes, and the researchers use those observations to retrieve optical light curves for the object. Between 2016 and 2019, its optical light faded by a factor of 100. Also, for a supermassive star, that's kind of a big deal. The object was undetectable in ground-based optical observation in 2023. So as we saw up there, it's from like the Keck telescope over in Hawaii. Yeah, it seems to be a lot small. Wow, looks like they're kind of even zooming in. Oh, no. Yeah, that's there. That's there. Hey, wow. Yeah, that's a big difference. The Hubble happened to image it in 2022 and found nothing in the optical and only a faint source in the near infrared. Wow, Hubble didn't even see it. Yeah. Well, near observation spectroscopy in 2023 with a Keck confirmed a faint near infrared source. Okay, so these are all the different observational things. And flux megajoules per megajoule years. I guess per megajoules per year. I think that's what's supposed to be, or at least that was obtained there. All right. Okay, so yeah, it appears to be going down. Yeah. Time modified for our Julian calendar. This figure presents observations from multiple telescopes over time, showing the object's dramatic fading. Okay. The quote, dramatic and sustained fading of this star is very unusual and suggests a supernova failed to occur, leading to the collapse of the star's core directly into a black hole, Dave says. Whether or not a star collapses directly into a black hole without exploding as a supernova depends on neutrinos, according to the authors. When a massive star reaches the end of its life, its outward radiation can't support its own mass. We covered that at the beginning. The star's core collapses and releases neutrinos, and the neutrinos drive a shock into the star's outer layers. I think I'm actually starting to maybe understand this for the first time. Because I kind of heard, oh, there's a lot of neutrinos. I'm like, we got a lot of neutrinos coming out. And isn't that just going to cause a beta decay in one way or another and instantly change a whole bunch of things? And if all of a sudden you're emitting, I don't know, whatever, electrons, antineutrinos, or neutrinos and positrons or something, and a whole lot of that's happening. There's a lot of stuff going on in that volume. Yeah, so I could see that. All right. So if the shock is strong enough, the envelope is ejected and the star explodes as a supernova. If the shock fails to eject it, the envelope is predicted to fall back onto the collapsing core, producing a stellar mass black hole and causing the star to disappear, the researchers write. The star started out with about 13 solar masses. Wow. Wait a second. Weren't they saying earlier for a direct collapse black hole? What is that like? Oh, 10 to the 5. That's 100,000 solar masses. Now again, they're talking about potential seeds, but I think we need to rewrite this article. Yeah. This is probably going to need some major updates. And again, it's like I just didn't really hear a lot of folks talk about it. Anton mentioned this and a couple of times, and I haven't heard anyone else. I'm like, isn't this a direct? We assume that this is a thing. Like supernovas are required, except in maybe really early particular scenarios. And it's like we're watching our galactic next door neighbor, and it seems to be happening right in front of us. It's been sitting in the data. Huh. And again, if this is true, that would also mean that, well, what? Maybe there's a lot more, quote unquote, invisible matter around. Might this explain where a lot of dark matter is coming from? I don't know. I mean, neutrinos are technically dark matter. It's weakly interacting and has mass. It might not be that massive. It's like 100,000, maybe 1,000,000 times less massive than an electron, whatever the heck that is. So we don't necessarily know. Okay, let's go back to our Universe Today article. Okay, so 13 solar masses versus, let's just plug it in. 10 to the 5 solar masses. What is that? Let's see. So 10 raised to the 5 solar masses divided. It's going to be 10 to the 4. 13 solar masses. Okay. So it's off by about 700 orders of magnitude. Listen, it's a big universe. It's a big universe. And It's not 122 orders of magnitude different. And again, you're going based upon the information you have. You have so much information, hey, you go buy it. Um, yeah. Okay. It's under 9,000. It is not over 9,000, so I think we're okay. That's my mimetic guess. Okay, let's continue. Oh, this is a nice little video. Oh, look at that. It's animated and everything. And I know Fraser lets us use all that stuff fair use. And I gave a link to the article. Okay, so basically that's supposed to be all that you have the outer shell there, and it's going to slowly gravitate in. It's going to create infrared stuff. And a lot of times we're not going to see a lot of wavelengths just because you still have the shell that's kind of still surrounding it, rather than being blown to basically smithereens across the galaxy and universe. Yeah. Stars with this mass have long been assumed to always explode as supernovae. They said the fact that it didn't suggests that stars with the same mass may or may not successfully explode, possibly due to how gravity, gas pressure, and powerful shock waves interact in chaotic ways with each other inside the dying star. Key point. Something we thought that maybe only happened early on with incredibly massive things, it appears to be an actual thing that happens. Did we solve the mystery of the missing stars? Can't say that yet. Astronomers know of one other direct collapse black hole candidate. It was observed in 2010 in NGC 6946, a grand design spiral galaxy about 25 million light years away. But it's about 10 times more distant than M31, that last one. The candidate named N6946 BH1. And its progenitor was also a supergiant star. It blossomed in luminosity and slowly faded, just like the object in Andromeda. The Hubble image on the left. Okay, so Hubble image on the left. Okay, 2007 of that star. And you go ahead about 8 years. Yeah, it doesn't seem to be there anymore. It seems to be disappearing. What's going on? Oh no. There might be a bunch of quote unquote dark gravity that has not been accounted for. Oh no. We might have to modify some models. Let's go cosmology. All right. Unfortunately, since N6946BH1 is so far away, it was much fainter, and the observational data isn't as high quality as the more recent one. We know that black holes must come from stars. With these two new events, we're getting to watch it happen. And are learning a huge amount about how that process works along the way. Said Morgan McLeonard, a lecturer on astronomy at Harvard and co-author on the paper. Oh, okay. Took a lot of effort to find M31 2014 DS1. We'll call it DS1. Why? That sounds cool. This work is the largest study ever done of variable infrared sources. They observed the stellar populations of Milky Way and other nearby galaxies looking for objects like this and found only one. Well, supernovae are hard to miss and announced their presence with months of extreme luminosity. Direct collapsed black holes are the opposite. Unlike finding supernovae, which is easy because the supernovae outshines its entire galaxy for a few weeks, finding individual stars that disappear without producing an explosion is remarkably difficult. The moment, the moment when you're like, something makes sense to me. Because I feel like a lot of times nowadays, it's very often one of the criticism of some scientists is you said a whole bunch of words. I don't understand the words coming out of your mouth. Now, if it's like the things that go kablooey, we can see. The things that don't have ginormous kablooey are harder to see. Makes sense. Okay, now astronomers almost missed this one, buried in mounds of astronomical data. The question is, how many more are out there? How common are they? Bingo. Comes as a shock to know that a massive star basically disappears and died without an explosion, and nobody noticed it more than 5 years. They said it really impacts our understanding of the inventory of massive stellar deaths in the universe. It says these things may be quietly happening out there and easily going unnoticed. Like many issues in astronomy and astrophysics, only a larger sample and better observations can advance our understanding of these direct collapsed black holes. The Vera Rubin Observatory has the potential to find many more of them in a decade long legacy survey of space and time. And thank you, Evan, for doing journalism. All I heard was I see a lot of quotes about what people said that were actually there. I see it's saying that, oh, Rubin Observatory has the potential, not like the Rubin Observatory was going to find all these. I don't sense an agenda other than science is cool. We have the potential to learn more. Totally love it. Evan Gow is a scientist, loving guy with no formal education who loves Earth, force, hiking, heavy music. He's guided by Carl Sagan's quote, understanding is a kind of ecstasy. Bravo, my friend. Wow. Okay, and this is why I'm supporting Universe Today or Fraser Cain's Patreon, just because I'm like, that's journalism right there, my friends. So whatever you think of that, better or worse, it's it. And this is what I told Fraser. I'm like, you guys aren't telling me what to think. You're just presenting it what it is. It's you don't have to start the title to your videos and articles with yes, look at this no good, very bad, terrible, horrible, no good person. It's like when you got to do a children's book title like Alexander, no good, horrible, very bad day. It's like, yeah, when you got to use all those adjectives and adverbs, I entertain the idea there might be a little bit of opinion in there. And again, it's one of the reasons why I did that little video earlier. It's like monetize news, monetize opinion. Just make sure they're labeled. Who would have a problem against that? Unless you're attempting to put your opinion out there as fact on the internet. And we know nobody would ever do that. And again, hey, you can do that if you want. I'm just saying that just label it opinion. It's not like you're trying to lie to your audience or anything. You're not trying to be a deceiver. It's not like you're just saying things because people give you money because they want to hear it. It's not like labeling an opinion instantly changes somebody sharing a video or story to instantly having the ability to say, well, that's an opinion rather than fact. But everybody's doing it. Yeah. And our current situation, is that really surprising at all? Not to me. Makes perfect sense. What are we incentivizing? We incentivize people to just run their mouths. I'm just saying, monetize news, monetize opinion. Simply label them as such. It's the Tommy Boy principle. Just put it on the box. That's all. It's again, what are you gonna say? I'm sorry. I'm sorry. I'm obviously seeking conflict. I need to go fight with other animals on the internet to get it out of my system. Uh XYZ, I resemble that because you have to be careful. If you're honest with yourself, you start to realize and notice things. And sometimes they say, what is it? Ignorance is bliss. Because when I start to understand and just take it, just extrapolate shortly, I'm like, oh my gosh, I've caused so much horror and terror in people's lives. I haven't even realized all the terrible things I was doing. And whether it was inadvertent or not, it's like sometimes it's just laziness. Oh, well, I'll do that later, blah, blah. And that led to all these extra dramatic things and it costing more. And it's like, why did I do that? It's okay. So again, I'm not a psychologist or quantum mechanic or anything like that. I'm a crazy person on the internet, but yeah, of course, the articles are in the doobly doo below. Feel free to check them out for yourself. That's about all we got. So Of course, for all those who are watching now, and for those who may be temporally watching in the future, take care of yourselves. Peace out, everybody. It's a wacky and wild world out there, and it's hoping for a better tomorrow, my friends. Peace out, everybody.